So we're going to have a look at the base graph, then we're going to investigate the transformations, and then we're going to look at solving equations using exponential functions. So that's what we're headed for. Can I get you, if you're not confident, just do it in pencil or on a scrap bit of paper. Can I get you to draw the base graph of an exponential function? Can you remember what features an exponential function has, what it looks like? Draw it there, draw it down somewhere. See if you can get that down. So the heading can be exponential functions, and then you can write the word base graph or parent graph, and then you can draw one in. Everybody's, but this is what you should have. You should first of all, well, I didn't actually state what that graph is, so it's along the lines of y is equal to b to the power of x for some base b. Okay, so what you should have had, and hopefully this will at least ring bells, is an asymptote, a horizontal asymptote that is y equal to 0. If you didn't have that in, explicitly have it in, then you need to write that in now. So an asymptote at y equals 0. And that is because there is no value that I can raise b to and get y equal to 0. So it is a non-value for the function. It doesn't work. When x is negative, y is extremely small, and when x is positive, y is extremely big, and so we have this kind of behavior here. It exponentially grows. Everyone good with that? Last critical piece of information is that y-intercept. What is the y-intercept?
When x equals 0?
Yeah, exactly. So when x equals 0, what's y equals b to the power of x?
1.
Yeah. Sam? 0, 1 is the x-intercept. I hope that's y-intercept. I hope that's not too small for you down at here. Okay, that's the base graph. I've got two shapes there, so two graphs though, because there's in fact two shapes for the exponential graph. Sort of. And I'll come back to what I mean when I say sort of later on. The second form looks like this. Asymptote at y equals 0. But this one goes like this. Is that ringing a bell for you? That's also got a y-intercept of 0, 1. This one is called a growth graph. And it's when b is greater than 1. So b is bigger than 1. The second one, what's the opposite of growth? Starts with D, rhymes with decay. Decay. This is what I'm reduced to doing. This is a decay graph, and it's when b is a fraction. So much easier to say b is a fraction than to write this if you're not confident with interpreting it. If b equals 1, there's a name for that kind of graph too. If b equals 1, the graph is called boring. Okay, because when b equals 1, it's a straight line. Okay? You know what? It's got a bit of a more proper name. The graph is trivial, we call it. And that's kind of a bit more an official way of saying it. The graph is trivial if b equals 1. And if b equals 0, we've got a name for that as well. That's also boring. And if b is negative, well, actually, when b is negative, it's not boring, it's extremely interesting, but we say it's not defined because the behavior of the graph is, and this is another official maths term, the behavior of the graph when b is negative is weird. So we don't worry about B when B is negative. So it's either it's above 0, but if it's a fraction, it's a decay graph. It's bigger than 1, it's a growth graph. Okay, this should all be stuff we have talked about, well, you have seen in a previous year. Anyone got any questions? Great, moving on. So, what we don't tend to do is talk about the domain and range. I've got it written down there for you already. The domain of the base graph is x could be any real number at all, except for 0. And y could be, oh, that's not right, is it? That's not right. Someone tell me what that should be for the, I've got the domain right. The range, I don't have right on purpose.
Orbital positives.
Orbital positive, that'll work. A couple of you said that, so well done. So it should have a little plus there. I do admit to mistakes, that was actually a genuine trick. Or if we want to write it in notation, in interval notation, you could go 0, oops. You could go 0 to infinity, like that as well, that will be fine. The interval notation for the domain is a little bit more painful, so I wouldn't use interval notation. Don't write it down, but it would look like this. X is, x can be 0. What am I talking about? Sorry. X is actually orbital numbers. That's my bad. That was definitely my mistake, my fault. So x can be all real numbers. There's no value of x that is restricted there. Okay, so it's all real numbers. The range is all real positive numbers. Can't be 0. Anyone got any questions on that?
Are you meaning the domain for the growth or the decay?
Doesn't matter. Genuine question. Sorry, yours was a really good question, so I'm throwing it back to you. Does it matter? Is the domain different between the growth and decay graph? No. Any value, any real number can be input into the function.
Oh, so it's the domain for both.
Yeah, it's the same domain for both. What about the range? Do I need to split that up depending whether it's decay or growth? It's a different shape, so surely the range would be different. No, it's not. The range is the same as well. Literally, if you have a look at both graphs there, even though one is starting with y very big and going to y very small for decay, and the growth graph is starting with y very small and then y getting very big, it's the same set of numbers that it's going to. And the last thing I'll put this is your old pal, 1 to 1. Is it 1 to 1?
Yeah.
Yes, indeedy doody dandy it is. It is a 1 to 1 graph, isn't it? In other words, it passes a horizontal line test. Okay, cool. So I thought I might just mix things up a little bit. I think we've got time to do this. Hopefully I won't be proven wrong. What I'm going to get you to do now is a bit of a self-exploration for a few minutes. So grab one of these sheets I'm passing around. Grab one of these sheets and pass it around is what I meant to say. And what I'm going to do is, now that we've looked at a whole heap of functions, and hopefully we're getting a decent understanding of how transformations affect properties of the graph. What I thought I might get you to do is to see if you can fill it out for yourself and determine what those transformations are. Now, I do have a little bit of assistance for you though. What I'm about to put onto Google Classroom, and I haven't done this quite yet, is I am going to send you a link to this document here, this Desmos graph. It's already been filled out for you, and you can see that it's got y equals b to the power of x as the base graph, and I'm just using b equals 2, and don't change that. We're gonna worry, because b is the base. Like every exponential function has a base number, the b. What we're interested in is a, which affects the vertical dilation, or the dilation in the direction of the y-axis, n, which is the horizontal dilation, the dilation in the direction of the x-axis, h, which is the vertical translation, and K, which is the horizontal translation, and then the sign of A affects whether it reflects, and the sign of N also affects how it reflects. And what I want you to do is I want you to basically leave all the values bar 1 alone, and then see what happens to the base graph when you adjust it. So we'll do the first one together. The first one is, we'll do this, actually I might have, yeah, no, we'll do the first one, which is the horizontal, the dilation in the direction of the x-axis. I think I've got that right, isn't it? Yeah. So the dilation in the direction of the x-axis is when I move n. So as n gets bigger, and you can see what you have to say is, what does it affect? Does it affect the asymptote? No. Does it affect the y-intercept? No. And it's not affecting the x-intercept either. Okay, so does it affect the domain? No. Does it affect the range? No. So that's what you're going to do for each one. That was a simple one, right? But you're then going to return this back to its original, which is 1, and then you're going to do the same thing for a vertical dilation, which is A, and then go through the other ones as well. Okay, and it's not an alone task. You can do it with the person next to you and stuff like that, just so you can get a sense of it. So I'm going to share that with Google Classroom now, and I'm going to give you, say, 5 minutes to see how fast you can get through it. Now, full disclosure, I just did those from my head. Charlie helped me, said that I missed one, so there may be others I missed. I think I've got it right, though. I didn't look at Desmos when I did it. I just did it from the top of my head. I think that's the full list, I think. Just tell me if I've missed something or I've said something dodgy, because it's very possible. Just to note, though, that we've kind of looked at each of these transformations independently. So you can sort of see from that that if I had a vertical transformation and a reflection, vertical translation and a reflection, it may very well affect an x-intercept sometimes, and sometimes it doesn't, kind of thing. So just be mindful of that. There is that transformations affect each other, I suppose. So there may be a multiple effect as a result. Note that the domain never got affected, did it? So the domain continues to be all real numbers, and there's nothing we can do to transform that function to change it to something else. You can deliberately restrict it. So if I was doing some sort of function that was in real life, and therefore x equals a negative number doesn't work, that would be a restriction of the domain that we impose upon it. But in terms of the fundamental, there's nothing to do there. Alrighty, so a couple of little notes I wanted to make. I think I've got it on the next page, and I'll use Desmos to sort of tease it out. So note 1. When b is a fraction, that's what that means. When b is a fraction, this is the same as a horizontal reflection of its reciprocal. Oh. I'll show you what I mean in a ticky. Horizontal reflection means it is reflected about the y-axis. So if we have a look way back in that first set of notes, I said there are two functions. There's this one here, or form of the function. This one here when b is greater than 1, and this one here when b is a fraction. Now that we've done a fair bit of work on different functions, can you see that both of these are actually reflections about the y-axis of each other? So in other words, a decay is just a flipped growth, and a growth is just a flipped decay. They flip around the y-axis. So it's the n value. It's the dilation about the y-axis. So it's a horizontal dilation. The reason why may or may not be obvious. I can show you visually first, and I'll show you graphically, analytically. So if I go here, if I have b equal to 2, you can see that gives me this shape here, when we've got 1, 2 being the position here. If I make b equal to a half, which is the reciprocal of 2, we can see we've now got -1, 2 being the position here. So the 1, 2 has reflected to -1, 2. That's what a reflection means. A horizontal reflection means all the positive x's become negative x's and the y remains the same. So that's gone to there, and we've got this decay happening instead. Okay, if I then reflect that, so if I make b equal to negative a half, no, I did the wrong thing. So if I leave b as a half and make n -1, so it's a reflection only, then you can see that this graph has gone back to 1, 2 again. Okay, so the reflection, b to the power of reflection, makes it reflect back. Okay, analytically, this is what's happening. So when I say analytically, I mean by using algebra, we can analyze that. So if I had a third to the power of x, then I can write that as 3 to the power of -1x. Okay? I'm hoping that's ringing a bell because I can't afford to go through index laws multiple times. But the index law is basically 1 over a to the n is equal to a to the negative n by definition. That's the index law. So all I've done is I have brought the 3 up and made it a -1 power. And then that, of course, is equal to 3 to the negative x. So a third, and oops, not x, my bad. That would be a little bit too dodge. So a third, its reciprocal is 3. The reason why 1/3 to the power of x is equal to 3 to the power of -x is because of this middle step here is what we do. Okay, so if you have a fraction, you can always turn it into a horizontal dilation. In other words, you can make it into a whole number if it's a one-on number and make it a -x instead. Okay, note 2. A horizontal translation is the same as a vertical dilation. A horizontal translation is the same as a vertical dilation. I'll show you what I mean and then I'll go through the example again. So here, I'll just return this to b equals 2. Okay, so we're back to normal. That's my normal graph. I'll turn off the base graph so it's less confusing. So if I translate by 3, so that's h equals 3. Like so, that's a horizontal translation. Oh, am I going to make it hard for myself? I'll make it easy for myself. If I go to h equals -3, like so, the graph is now like this instead. Okay? So this would be the graph y equals 2 to the power of x plus 3. H is -3, that'll make it x plus 3. So that's just translated across. But, and I'll explain why it works in a second, if I now make h equal to 0 and instead make the value of a equal to 8, we can see that same point is there. Okay? It's the same point. Or it goes through the same point, I should say. The actual points have stretched up ways, but it goes through the same point. So it's the same thing. And I'll explain why now it is the same thing. I'll just pop this back to normal. The reason why, and maybe you're ahead of me, in which case that'd be great. The reason why is because I can take 2 to the power of x plus 3, and I can convert that to 2 to the power of x multiplied by 2 to the power of 3. This is also a basic index law. I'm just using it in reverse. A to the power of n times a to the power of m is a to the power of n plus m. 2 cubed is 8, and so it's the same as 8 multiplied by 2 to the power of x. Okay? So in other words, a translation 3 units to the left is the same as a dilation 8 times vertically. It does the same thing because of the way index laws work. It also means, PS, if it makes it easier, if you can see that you've been given a function like this, y equals 8 times 2 to the x, you can use this law to make it into a more basic function if that would make it easier for you to graph. You could absolutely do that. Alrighty. Any questions? Okay, 2 quick examples and then we'll get going. So, sketch y equals negative 2 to the power of x minus 1 plus 1. So we can see there's a reflection there. We can see there's a translation 1 unit to the right, and there's a translation of 1 unit up. Okay, so we can see, like in your head, just visualize, I'll do it in red over here, just visualize that you can sort of see, well, it's going to reflect. So instead of doing that, it's going to do that. It's gone up by 1 unit, so my asymptote is now up here. And it looks like I'm going to have, therefore, a y-intercept and an x-intercept. I don't know what it is yet. So you're visualizing that just so you can get ahead of it, and now you can put down the critical information. The asymptote. Y is equal to 1. We get that straight from the vertical translation. Shape, if that helps, is going to be like that because it's reflected about the x-axis. Y-intercept. At x equals 0, we have the y-intercept. Y is equal to negative 2 to the power of 0 minus 1 plus 1. That's 2 to the power of minus 1 is 2 to the negative 1. 2 to the negative 1 is a half. So I'm going to have a minus a half plus 1. So that equals a half. I did a lot of that verbally because I'm hoping your index laws are strong enough. Okay, so 2 to the negative 1. 2 to the negative 1 is the same as 1 over 2. That's where I got the half from. X-intercept. At y equals 0, we have 0 equals negative 2 to the power of x minus 1 plus 1. Subtract 1 from both sides and we get minus 1 equals minus 2 to the power of x minus 1. That means that 2 to the power of x minus 1 is equal to 1. Where do we go from there, team?
Isn't the y-intercept 0, half?
That correct. I'm now doing the x-intercept. The y-intercept is... Oh, sorry, I wrote that down wrong. That's what you're saying. Okay, cool. Yep. 100%. Thank you very much. Now, x-intercept, where do we go from here, team? You can't touch your calculator, not allowed to. Excellent. So you can do it literally or just do it, but remembering that 1 is equal to 2 to the power of 0, well done, Pip, we can now say x minus 1 equals 0. So we call this equating powers or equating exponents, and so x is equal to 1. I didn't leave myself a lot of room to graph here. I have to do it in this little space here. So x equals 1, y equals a half, and so our graph, you do a much neater job than I. Please do as I say, not as I do. We've got y, we've got x, we've got a y-intercept. I then draw in the line. I then label. I draw before I label because then I don't miss it, kind of. So this would be 0, a half, and this would be 1, 0. And again, we've got enough information on our graph. We don't need to find another point for scale. We've got enough points there for scale. Before I got you to do practice, I had this example 2 up, and it was this graph here, and I said, how would you go about figuring it out? And as always, it comes down to just putting in the information that you do know and then figuring out the rest. But this sort of problem has a couple of little tips and tricks to it, which is really important. First thing is this. With the information that you're given, it is quite challenging to work out the base. When I say the base, I mean b to the power of whatever. So you need to know from your course document b is either equal to 2, 10, or a special value we're going to have a look at on the other side of the progress test called the called e. And we'll look at that later. You don't need to worry about what e is at the moment. So if you're not given b, you can pretty well much do a guess and check. You can put in b equals 2, does it fit the information? If it doesn't, try b equals 10. Does it fit the information? If it doesn't, try b equals e, and does it fit the information? So that's good enough. There are more sophisticated methods for working out the base, but we don't have to do them in this course. So you can effectively just have a bit of a guess and check. To jump the system a little bit, I'm going to tell you that b is equal to 2, but we will confirm it. B equals 2. So we would start off with y is equal to a multiplied by t to the power of, and I'm going to just show you what I mean by putting in some information here. This is what makes it tricky because I can only verbalize it really. I can see that this is a decay graph, right? So that means that I can see that this is a reflection about the y-axis. It's a horizontal reflection. Okay, so that means I'm going to have a negative x. I can also see, and I'm going to zoom up for this so you can see it, I can also see that the coordinate minus 1, 1, I know enough about my base graph to know that minus 1, 1 in the base graph would be 0, 1. So in other words, I've gone back 1 unit. Okay, so in my graph, I can translate, I didn't mean to be making you feel sick then. In my graph, I can translate that to a minus x plus 1. 1 unit to the left, reflected. Okay, reflected. I don't have my brackets around it because of the order in which I'm applying the transformations. Okay, I'm applying them backwards. 1 unit to the left, and then reflected will give me minus x plus 1. K is just y equals minus 1. So we've got k is equal to minus 1. So that's a pretty good start. Just based upon the information and my knowledge of transformations, I can, as usual, pretty much get it down to I need to figure out what the dilation is, if any. And there shouldn't be, but I'll double check. This is the bit I actually haven't done properly, so I hope this works out. And if it doesn't, I'll explain why it doesn't. I know why it might not. So there's one other point I know. What is it? I've used minus 1, 1 already. What's the other point?
Y.
Yeah, 0, 0. Now, y is not a point. It's a variable. So 0, 0. So I'll substitute 0, 0 in. And again, if this doesn't work, I'll tell you why. I think it should. Just doubt myself sometimes. A multiplied by 2 to the power of minus 0, which is 0, plus 1 is 1, minus 1. Add 1 to both sides, and I get 1 is equal to 2a. And then I divide both sides by 2, and I get a is equal to 1/2. Okay. So, in other words, y is equal to 1/2 multiplied by 2 to the power of 1 minus x minus 1. I'm not feeling confident about that. I feel like I'm going to have to come back to that one, but I think it's right. We okay with that so far? We can do better than that though. Yep.
I thought there was a way where you would put 1 into y and then you'd sub negative 1 into x. Can't you sub it?
You could. But I'll look back into that M. The reason why I didn't is because I've already used that information here, but I might not have used it properly, but I think it's okay what we're doing anyway. So I'll put a pin in that, I'll come back to it. Okay, so we've got y equals a half multiplied by 2 times 1 to the minus x. But when you see a half sitting out there, you could turn that into 2 to the negative 1. Like so. And then you could use your index laws. I'd just be doing this in my head, but I'm doing it for the sake of it. Like that. And then that would give you 2 to the negative x minus 1. Now, like I said, I set this equation up and then I solved it without preparing it beforehand, which means I didn't necessarily do this in the most efficient way. That's what happened. This is mathematics at the coalface where I'm just doing it based upon what I know. There might be a bit more of an efficient way of doing that. I'll have to think about it a bit more. But it gets you there in the end. Okay, so that's basically it. For that problem, you just set it all up and solve away. Any questions? Okay, cool. Next thing, and the final thing for this. I'll give you practice next lesson, but we're just going to set it up now. Exponential equations. One of the things that you did last year as well, and we need to do this year, is to understand exponential equations and how to solve exponential equations. So here's an example. 5 to the power of 2x minus 4 is equal to 25 to the power of x plus negative x plus 2. That's the problem. I'll take you through the solution because it's fairly straightforward. Effectively, what we want to do is we want to equate, without using a calculator, obviously. With a calculator, we just put it in and solve it. Use logs, that kind of thing. But generally speaking, analytically, what we want to do is we want to express both sides of the equation with the same base, and then we can equate the powers, equate the exponents. So 25 is 5 squared, yep. So we would go 5 to the power of 2x minus 4 is equal to 5 squared. Notice how I'm putting them in brackets, to the negative x plus 2. Now the next index law we have to use is that this is like an expansion. You have to multiply each thing outside by the thing inside. So that would be 5 to the power of 2x minus 4 is equal to 5 to the power of negative 2x plus 4. Yeah, I distributed the 2. And now I can equate. I can say 2x minus 4 equals minus 2x plus 4. Add 2x to both sides to get 4x. Add 4 to both sides to get 8. And so x is equal to 2. So that's how you do exponential equations. You get the bases the same, equate the coefficients, equate the indices, and then you're able to solve. If you can't get the bases the same, and you might need to do some manipulations to get them the same, more than the simple one I just did. If you can't get the bases the same, you're really stuck with having to use logs in order to solve it. But when you can, They're usually relatively straightforward. Okay, that's it. So I'm going to give you some more practice now, which is exercise 5C. Question 2, AEH. Question 3, AEH. Question 4. So you can have the rest of the lesson to practice that. I'll let you know when it's 1 o'clock and time to go, and that will do.